Welcome to Lecture 33. This is basically illustrating Green's theorem and applications. And Green's theorem, in this case, is the circulation form in 2D. The material covered in this lecture comes from Reading Assignment 4, Section 4.2.3. And the objectives of this particular lecture are to discuss applications in which Green's circulation theorem is utilized. And secondly, to illustrate Green's circulation theorem for computing an area, and particularly the area of an ellipse. Now, we didn't discuss applications of Green's flux theorem because they don't come up that frequently in terms of physical problems. But in this case, Green's circulation theorem does come up frequently in applications. So the concepts and visualization skills are more or less understanding how to work with Green's circulation theorem. By the way, this is the last lecture. There will be 4 review lectures coming up after this, but this is the last official lecture for this course. As usual, the second slide is just a summary of the slides to follow, so we'll just skip over this slide and move on to the next one. Okay, so we'll look at the applications and 3 illustrated examples. You'll notice here that I've got things blocked out. The items highlighted in red and orange are discussed in this lecture, but the only testable material is the object highlighted in orange. The last item, which is the derivation of Green's vectors, identities, 3 in total, we're not discussing here, nor are you responsible for it, but if you're interested, it's basically in section 4.10 of Reading Assignment 4. So what we'll be looking at is Huygens Principle of Diffraction, just as an example, in terms of where Green's circulation theorem comes in handy. And it uses the divergence theorem and Green's third identity in terms of coming up with what is a very simple solution to a complex problem. We won't go into details. I just want to sort of give you a motivation as to why these theorems can actually be very useful in a physical context. Secondly is the proof of Cauchy's integral theorem for complex variables, which you basically discussed in MAT290 earlier this term. Here I basically will show you the details. You're probably in a position now to understand these details, given that you understand Green's circulation theorem. And the part that we'll be interested in and is testable material is to compute the area enclosed by a contour, and the example we'll illustrate is that of an ellipse. And as I mentioned, the derivation of Green's vector identities, 3 in total, will not be discussed in this lecture. All right, so Huygens principle, I've just shown a simple diagram here. This is a classic diffraction pattern that you get if you've got basically a plane wave of light that basically strikes a plate with a small slit in it. And if you look at the output, you basically see the waves basically propagating outwards. And if you were to measure the line intensity in a vertical direction, you would see places, locations where you have constructive interference and destructive. Constructive, you'll see light intensity that's large, and destructive, you'll see very light intensity just is quite weak. And so this problem basically is a classic problem in electromagnetics. It can be solved sort of by the brute force method, but in fact, there's a much more elegant way to approach it. And again, you need to make use of Green's theorem and some identities to be able to reduce it to a simple problem where you can replace this plane wave coming in here by a series of spherical wavefronts. So this is something that produces spherical waves along here, and then by superposition you add all these up, and the addition of these basically will produce the pattern that you see out here. This is a much simpler problem to formulate. In fact, there are a lot of textbooks that basically go through the details of it. We won't. I just wanted to show you that this theorem can be used to take a complicated problem and basically make it much, much easier. And so we'll just leave it at that and we move on. I'm more interested in going Cauchy's integral theorem for complex variables, which you've already basically discussed in the MAT290 course, but I'll just revisit it here because now that you have Green's circulation theorem, you can see how it plays a role in the derivation. So we start by saying let z be some complex number, x parameterized in terms of some t, plus I, y of t, I being the imaginary number, and let f of z be some real component, p of z, plus imaginary q of z, and let r, which is a position vector, you might say, parameterized in terms of variable t, have components x and y, and that you've got a lower limit on t and an upper limit of t. If you take the derivative with respect to t, then we end up with r dot x dot t and y dot t. And then if we're talking about a contour integration, then the tangent vector, basically ds, would be r dot dt, right? Or you could also write this as capital T bold ds, but we just leave it in this form. All right, what would dz be? Well, in terms of t, this would be just dz equals dx, x prime with respect to t dt, plus I, y prime t dt. All right, so this is more or less the information that we start with. Then we're going to basically apply a closed contour integral to this complex entity, f z dz, and so we just substitute in as expected. So f of z is replaced by p of z plus I q of z, and d of z comes from here, is replaced by this entity here, and dt is a common factor, so we just bring it out. Then what we do is we basically take this expression and expand it out, and so that we have real terms for this integral and imaginary terms for this integral. So there are 4 terms in total, 2 of which are real and 2 of which are imaginary. So what we can do is we can look at this now and write this out in a vector dot product notation form. So if we basically consider P and Q as an x and a y component of a vector, right, and x dot and y dot is a second vector, with an x dot being the x component, y dot being the y component, then the dot product between these 2 vectors basically gives you this result. Similarly, on this side, we'd have a dot product between these 2 vectors. But x dot t, y dot t dt is, according to work we've done before here, is just going to be equal to ds. So that can be replaced now by dot ds. So pz minus qz dz plus I qz pz dot ds. So this is in a form now where we can apply Green's circulation theorem. All right, so we take a contour integral, closed contour integral, and replace it by an area integral. And so these are the components of the vector. So this would have been normally would be f and g. And so we just basically go ahead now and, using the circulation theorem, compute the right-hand side. So this term becomes this term, and this term becomes this term. But from your MAT291 course, right, you have the Cauchy-Riemann equations, which are the ones shown here. dqx equals minus dpy, dpx equals dqy. Right? And also, and that a complex function f of z is analytic on a region, i.e. the complex derivative, which is shown here, exists in a small neighborhood of each r, if and only if fz satisfy the Common equations in R. Okay, so general conclusion, and therefore analytical functions, both integrals are identically 0. If you make the substitution here, for instance, dqx plus dpy, dqx is minus dpy, so this term becomes 0. dpx equals dqy, they're equal, but subtract, that gives you 0. So that the resultant basically is 0. So finally, the theorem is Cauchy's integral theorem. Let R be a closed region in the plane with a smooth boundary C. We allow the boundary to be any finite number of simple closed curves. Then if f of z is any complex function which is defined and holomorphic, which means analytical, this is just another way of saying it, on all of R, then we can say that the closed contour integral fz dz is equal to this, is equal to 0. So effectively, this is equal to 0. So that's basically the outcome. All right, so the more interesting one is the application of the Green circulation theorem in terms of computing the area of a region. And so we're going to basically do a little thought experiment here. We're going to say consider 2 vectors. One of the vectors is 0x, and a second vector is y0. And so we're going to apply Green's circulation theorem to the left-hand side and right-hand side for both vectors. So here is Green's circulation theorem. And so we're going to basically do this computation for this and do this computation for this and basically do a comparison between them. So we're going to parameterize a contour and determine TDS. So if we set position vector R as having a component x and y parameterized in terms of variable t, then the derivative of this respect to t is x dot ty dot t. The unit tangent vector that's tangent to the contour would be r dot over the magnitude of r dot, and ds, which would be magnitude of r dot dt. Or TDS is r dot dt, and you can write this out in explicit form. This will just become dx dy. So let's go through each one of the cases in turns. First of all, consider the case when f is 0x. In that case, if we take the derivative of g with respect to x, which is the y component, derivative of f with respect to y, which would be the x component, then for this case, gx equals 1 and fy partial equals 0. And so we just make the substitution, f is 0x, dx dy. And in this case, we end up basically with the closed contour integral just being x dy on the left-hand side, but on the right-hand side, this just becomes the integral over the region. So this is more or less the area. Let's take case 2. In this case, the vector is y0. If you then do the partial derivative calculations, we end up with g of partial x equals 0, f partial y equals 1. And if we now do the closed contour integral with the new f, which is y0, TDS remains the same. It's still dx dy. If you take this dot product, this is y dx. If you now compute the right-hand side, then you end up with minus integral over the region, which would be minus the area. So we can essentially say, we can conclude that x dy equals minus y dx equals the integral over the region, which is in fact the area. Or we can do a hybrid. We can essentially that the area, which is the integral of dA over the region, is 1/2 closed contour integral of x dy minus y dx. So this is just another way basically of writing things. You can either say this or this or this. But this is a particularly useful form, and we can use this then when we're doing, for instance, calculations of regions, an area, which is bounded by a contour. We can work with the contour integrals and essentially come up with the result, which is in many cases easier than having to actually do the computation of the area. All right, so let's take the example of computing the area of an ellipse. The problem statement is find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. First of all, we have to parameterize the ellipse contour. So we're going to just choose x to be equal to a cos t and y to be b sine t. T will range from 0 to 2 pi, and this will trace out basically the elliptical contour. All right, so now we have to compute the components of the differential length vector, which is dx's and dy. Dx is dx dt dt, and if you do this computation, this just becomes minus a sine t dt. So dx dt meaning you have to take the derivative of this with respect to t. For dy, this is dy dt dt. You're taking derivative of this with respect to t, so this becomes b cos t dt. Next step is to compute x dy minus y dx. And so we know what dx and dy are. Here they are. We have x and y. We know what that is because x has to be in terms of a cosine t and y would be b sine t. So making the substitution for this and for this, which is what you see here. So that is this term and this is this term. Simplifying, you end up this as equaling ab dt. So the last step is to compute the contour integral 1/2 this x dy minus y dx. So effectively, this ab is a constant, so it comes outside the sign. The half is there, and your integral dt from 0 to 2 pi. And this is pi ab, and this is the area of the ellipse. A very simple way of doing it. Doing it this way, where you basically work with area, would be a little bit more involved. So we have now two techniques for solving the area. One is basically using the outcome of Green's circulation theorem, involving contour integrals, or we can basically, by brute force, do the calculation of the area using a double integral. So that concludes lecture 33. Thank you for listening. The next series of lectures will be review lectures, but this more or less concludes the course. Thank you.